Hello everyone, my name is Itay Tsabary, and I'll present a work titled MAD-HTLC because HTLC is crazy cheap to attack. HTLCs are smart contracts used in many cryptocurrency systems, like the Lightning Network. However, they are known to be vulnerable to minor bribery attacks on Ethereum. In this work, we show these attacks are simpler, cheaper, and apply even to Bitcoin. We also propose a solution, MAD-HTLC, which is practical, secure, and incentive compatible. This is a joint work with Matan Yechieli, Alex Manuskin, and Itay, and you can find the full paper in the Proceedings of IEEE Security and Privacy 21. I'll start with some background. So, cryptocurrency systems facilitate transactions of internally minted tokens among their users. They use the blockchain as the main data structure. These systems are operated by miners. They include transactions in blocks and in return receive transaction fees. They are incentivized to optimize their transaction choices. We refer to these optimizations as miner extractable value. The system tokens are associated with contracts. These are predicates evaluated on transaction data. A value transaction must satisfy the contract's predicate. We say a transaction redeems an input contract once it's confirmed, and each contract can be redeemed only once. Hashtime block contracts, HTLCs, are contracts established by two users, Ant-Man and Batman. They include the cryptographic hash function's output and the time OT measured in blocks. HTLCs are the basic building block for many cryptocurrency constructions, like off-chain payment channels, atomic swaps, contingent payments, and so on. The HTLC predicate states that Ant-Man can get the tokens by revealing a matching preimage, or that Batman can get the tokens after the timeout elapses. We refer to these as a hash lock and a time lock, respectively. Consider an HTLC instance initiated on block X. Batman can get its tokens starting only at block X plus T, and only if they hadn't been taken yet. We call the miners are those who pick which transaction is included and in which block. The cryptocurrency constructions that use HTLCs make the following assumption. If Ant-Man publishes a redeeming transaction before the timeout, then that transaction is indeed included in the blockchain. There is a known issue here. This assumption neglects miners' incentives, specifically their MEV optimizations. This misalignment opens a bribery attack opportunity for Batman. Instead of doing nothing, he can bribe the miners to exclude Ant-Man's transaction until the timeout elapses, and then to include his transaction instead. Intuitively, consider an HTLC contract holding 5 tokens, and Ant-Man's transaction offering a single token as a fee. According to the assumption, the miners include Ant-Man's transaction, so Ant-Man gets 4 tokens, Batman gets none, and the miners get 1. However, if Batman decides to offer a higher payout, say 2 tokens, then the miners are incentivized to take his transaction instead, resulting with 2 tokens for them, 3 for Batman, and none for Ant-Man. This is clearly better for Batman and for the miners. Windsor et al. Suggested coordinating a bribery attack using elaborate smart contracts. Their suggestion applies only to Ethereum, but not to Bitcoin. It also requires prior deployment, meaning the attack has costs regardless of its success. They analyzed the required bribe to incentivize a single miner to support the attack, and show that if all other miners also support the attack, then that cost is independent in the time OT. However, if some miners do not support the attack, then the required cost is exponential in the timeout. This suggests that longer timeouts can mitigate these attacks by making them too expensive to execute. In this work, we present a simpler attack variation. We also tightened the result regarding the attack cost, showing it is independent in the timeout if all miners are rational. Our variation does not require a coordination smart contract, but simply uses the transaction fee mechanism. This makes it Bitcoin compatible, and means it requires no prior deployment, therefore it has no cost if the attack fails. For the analysis, we consider a game played by all involved parties, Ant-Man, Batman, and the miners. We consider rounds, or subgames, describing the creation of the T blocks. The suitable solution concept for this game is subgame perfect equilibrium. This captures the ongoing decision-making that all involved parties make throughout the game progress. As an example for SPE analysis, consider a game of tic-tac-toe. To decide the best action in each turn, the player simulates all possible game extensions, consider the possible outcomes, and chooses the action that leads to the desired result. Subgame perfect equilibrium is when each player is satisfied with their action in each step. This analysis technique is called backward induction. The game results are recursively propagated back to the decision point. Our analysis shows that the required bribe is independent in T. This means that increasing the timeout does not make the attack more expensive. We also found multiple instances on the Bitcoin network where the attack is extremely cheap and highly profitable. For example, we found several HTLCs holding over $26,000, where the required attack costs are only 2. I should mention that although the simplicity and high profitability, we are not aware of this attack taking place on Bitcoin as of today. This is probably due to the current MEV optimizations are still immature. So, even though today's miners do not optimize for this, that's hardly something to rely on. And the obvious question is whether we can prevent this attack. For example, what if Ant-Man counter-bribes? Well, in this case, Batman can counter-bribe, and so forth, resulting in a bidding war. Our analysis shows there is an asymmetry here, and that Ant-Man can win this bidding war with a fee linear and a secured amount, about 1% for realistic parameters. This is very expensive. Going back to the previous example, Ant-Man would have needed a $260 fee, which is 10,000 times more than what you originally offered. So counter-bribes are not practical. We need a systematic solution to this problem. We present MAD-HTLC. Recall the problem is that HTLCs don't consider miner incentives. So let's not do that anymore, but actually use the miners to enforce the desired execution and to deter attacks. Here is a quick overview for the remainder of this talk. First, I'll detail the MAD-HTLC contract and the security and the incentive compatibility proofs. Then I'll discuss our Bitcoin and Ethereum implementations and what happened when we deployed them on the main networks. Finally, I'll present our Bitcoin MEV infrastructure. The design principle of MAD-HTLC is mutual assured destruction. This is a notion from game theory, describing a setting where two parties refrain from attacking each other, as doing so will result with both of them losing. This is a deterrence mechanism, and in MAD-HTLC, if either Ant-Man or Batman misbehaves, then they both lose. The contract itself comprises 2 subcontracts: the deposit, which carries the main HTLC functionality, and the collateral, which is optional and only used to prevent spitefulness. The separation is only for Bitcoin compatibility, but the subcontracts can be consolidated on Ethereum. The contracts use a time lock and 2 hash locks, denoted by a hash lock 1 and hash lock 2. The time lock is just like the HTLC time lock, and a hash lock 1 is just like the original hash lock in HTLC. Hash lock 2, however, is an addition from MAD-HTLC. The deposit predicate has 3 redeem options. Either Ant-Man gets the tokens by solving hash lock 1. This is just like in the original HTLC. Or Batman can get the token by waiting for the timeout to elapse, like in the original HTLC, but now you also must provide preimage for the second hash lock. Alternatively, anyone can get the tokens by providing the 2 preimages for both hash locks. When I say anyone, I actually mean any miner. If a miner sees a transaction that reveals both preimages, she can just create a transaction of her own and take the tokens herself. This is actually an MEV opportunity. The collateral predicate uses the same lock parameters, but it is a bit different. Either Batman gets the tokens after the timeout, or any miner can get the tokens after the timeout by presenting the 2 preimages. So, is this secure? Why does it work? Our first step is to list the desired possible interactions that Ant-Man, Batman, and the miners can have with a MAD-HTLC instance. These include the creation, the initiation, and the redeeming of an instance. For example, we consider that redeeming using a hash lock requires the redeeming party to have the matching preimage beforehand, or that miners initially do not have the preimages and can only learn them if they are published by a different party. Now we prove these are indeed the only possible interactions. So we define an ideal functionality F, detailing the desired possible interactions in an ideal world. We also define a protocol pi that states how MAD-HTLC instance is created, initiated, and redeemed. This protocol uses the hash function in the blockchain, which we model as global ideal functionalities. So we consider the protocol pi in a hybrid world. The last step is showing the hybrid world with protocol pi and the ideal world with functionality F are indistinguishable. The possible interactions with the contract give rise to a game, played by Ant-Man, Batman, and the miners. We use subgame perfect equilibrium analysis and show MAD-HTLC is incentive compatible. No party gains by deviating. I'll give some intuition. Consider that only one preimage is published. Then the miners do not know the other preimage and can get the tokens. This scenario matches the intended behavior. However, if both preimages are published, miners will simply take the tokens themselves. This scenario describes either Ant-Man or Batman attacking. Also, note that if Ant-Man publishes his preimage, then Batman is unable to get the deposit tokens. So a spiteful Batman might just publish the second preimage anyway. This is where the optional collateral contract comes into play. If Batman does so, he will lose the collateral tokens, and if not, he will get to keep them. I'll now present some implementations and main network experiments. We implemented MAD-HTLC using Script for Bitcoin and Solidity for Ethereum. MAD-HTLC is slightly more complex than the original HTLC, so the interaction transactions are slightly more expensive. In Bitcoin, the additional costs are about a few dollars. For Ethereum, the basic implementation is a $150 overhead, but this can be reduced to about $10 for an amortized version. Please note the overhead is independent of the secured amount, which can be thousands of dollars. Taking as an example the $26,000 for Bitcoin contract, $5 are way cheaper than the $260 required for the HTLC counterbribe. I'll also mention that for the off-chain payment channels, the HTLC or the MAD-HTLC is only used when unilaterally closing a channel. This is not the general case and happens only if one of the parties is trying to cheat or becomes irresponsive. So even this lower overhead is incurred only if there is a dispute. We deployed MAD-HTLC on Bitcoin and Ethereum main networks. On Ethereum, some of our transactions were Fortran, showcasing MEV in action. This is expected as MEV on Ethereum is widespread. On Bitcoin, however, all our transactions were confirmed. We didn't observe any related MEV optimizations. So why don't we see MEV on Bitcoin yet? Is it because it's too hard? We show this is not the case by patching the popular Bitcoin Core client. Our first patch is to support the HTLC bribe attack, requiring only 150 lines of code. The code identifies Batman's bribe, delays Ant-Man transaction, and includes Batman's transaction after the timeout elapses. We also created a general MEV infrastructure. Using RPCs, it exports data to an outer Python module, where one can implement any MEV logic features. For example, we implemented the MAD-HTLC enforcement logic, a miner looking for a published preimage and creating a transaction of their own. This patch required 350 lines of code. To conclude, HTLCs are vulnerable on Bitcoin as well. The required bribes are cheap and the potential reward is high. The attack relies on MEV, which is easily implementable, and simply increasing the timeout does not help. We introduced MAD-HTLC, a simple plugin replacement with a minor overhead compared to the secured amounts. It is secure and incentive compatible, it's easily supported by miners, and its code is available online. Thank you.
Thanks for the great talk, Itay. Let's see if we have questions on the Slack channel. Let's wait for more questions on the Slack channel. Maybe in the meanwhile, I have a couple of questions that I can probably try to answer. So from what you said, it looks like the current blockchains are at a significant risk of HTLC attacks, especially given that it's very cheap to mount these attacks. So I was wondering if HTLC was actually a bad contract design to begin with. Are there other secure alternatives to HTLC that achieve the same functionality that HTLC provides? Or in other words, if you were to design the same functionality that HTLC offers, would you design a different primitive or a different way of doing things?
Yeah, that's a good question. So first of all, my student Itay Tsabary was not able to attend, so I'm Itay and I'm covering for him. I didn't massively change between the recording and now. As for your question, HTLC turned out to be a very useful primitive. It's used in a plethora of smart contracts. Payment networks are the most common and the most famous, but really, in any situation where two parties interact off the blockchain and then should settle on the blockchain at a later stage, we need really something similar to HTLC, because we need an operation to happen on the blockchain. This should be allowed because either party should be able to unilaterally settle the situation. But this ability of the party should allow the other party to refute this settlement in case the first party is cheating. And so this sort of interval is really a core technique for smart contract design. And the fact that the first transaction happens on the blockchain and there is some interval until the refutation happens, this allows an attacker to issue a bribe attack. There are no concrete alternatives I'm aware of outside MAD-HTLC.
I see. Thank you. I think meanwhile I have another question. So you also talked about like, did you also upstream your fixes to Bitcoin Core? Can you also elaborate a bit about that experience?
Mm-hmm. So the Bitcoin Core updates, we did two of those. First of all, we were curious why people were not using it. So we tried to figure out whether it was hard to take advantage of bribes against HTLC. And it turned out to be very easy. So the reason these bribe acceptance is not implemented is simply because it is, so far at least, not common, and miners simply didn't bother to implement it. Really took 150 lines of code, like Itay said in the recording. So this was trivial. What was more important for us was to implement the general MEV infrastructure that would allow miners to take advantage of MAD-HTLC implementation, and then protect users that use MAD-HTLC. This required getting a bit more involved, and it was important for us to make this accessible. So the actual programming of the logic is done in Python, and the Python drives the Bitcoin client to manage the contracts.
I see. Thank you. If you have more questions, please post them on the Slack channel. I think the authors will be more than happy to answer it there. Thank you so much for the talk.